Hello, this is Dr. Gardner. Today we're going to be looking at how to view equilibrium processes. Now when we look at a reaction that's at equilibrium, we usually use a double-headed arrow. This indicates that the forward reaction is occurring, but the reverse reaction is occurring at the same time. Now at some point the rate, the speed of the forward reaction will balance or match the rate of the reverse reaction. At that point we have reached what's called a dynamic equilibrium. We still have reactants going to products and we have products going back towards reactants, but that's occurring at the same speed. Now let's say we start with a container that has dinitrogen tetroxide in the gas phase. In that case it's a fairly colorless gas, but as we proceed to the right with this equilibrium reaction, we're producing nitrogen dioxide, which is a brownish yellow gas, and as we keep going forward towards the right to form the product, the nitrogen dioxide, we'll notice that the reaction with time becomes darker and darker, which gives us a physical way with that color change that we can observe forming more product. Now at some point as time passes, we form enough product that the reverse reaction rate increases, because remember, as I have a larger quantity of compounds involved in a chemical reaction, the rate of a reaction will increase, and so as more and more product is forming, we notice that it can recombine to go back to the left to go to the reverse reaction to form the dinitrogen tetroxide. So at some point we'll see that the color of the gas stops darkening, and at that point we have reached a dynamic equilibrium where the reverse reaction is occurring just as quickly as the forward reaction, and we are no longer seeing a net change in the amount of reactants or products at that point. Now we're going to look at a few diagrams that will help you visualize this in just a moment, but realize that once we have the concentrations of reactants and products constant, because the net change is not different for the forward or the reverse reaction because they have the same rate at equilibrium, that's when we have a dynamic chemical equilibrium that has been established. Now this is quite easy to see when you look at some diagrams. So let's say we're starting with the dinitrogen tetroxide, and it's the only reactant to begin with. So this graph shows concentration on the left-hand side here on the y-axis, and then I have that graph versus time as we proceed towards equilibrium. We'll notice we begin with just dinitrogen tetroxide, and we don't have any nitrogen dioxide to begin at the very beginning. Now as the concentration of the dinitrogen tetroxide drops, the rate of the reaction will be decreasing because that concentration is decreasing. But as we're forming product, the nitrogen dioxide, the rate of the reverse reaction begins to increase, and at some point we are consuming the dinitrogen tetroxide as quickly as we are also using nitrogen dioxide to go in the reverse reaction. At that point the concentration of reactants on the left hand side of the reversible reaction is being consumed as fast as we are forming the reactants from the reverse reaction, and so we see no net change in concentration. So where we see no net change in concentration, the forward and reverse reaction rates have matched one another, and we no longer see a net change in concentration. So where these lines level out in concentration is when we've reached equilibrium. So this dotted line indicates when the equilibrium process has been established, where we have no net change in reactants or products. Even though I have the forward and reverse reaction occurring, their rates are the same at that point. So if we were to graph rate versus time, what we could see is the rate of the reverse reaction is increasing as the concentration of the products on the right hand side are becoming greater, and the rate of the forward reaction is decreasing as we consume some of the reactants. And at some point those two rates are matching one another where the dotted line is, and that's where we achieve equilibrium. There's no net change in rate for the forward or the reverse process at that point, and that's where we were seeing our concentrations are maintaining a constant concentration on the previous graph. So realize when we've reached chemical equilibrium, we see no net change in concentrations. We have the rate for the forward reaction equal to the rate of the reverse reaction. That's what we're looking for. Now oftentimes we'd like to mathematically show what's going on with equilibrium, and we'd like to look at a ratio of reactants to products when we're indicating that we've reached equilibrium. Now that ratio of reactants to products can be expressed as what we call an equilibrium constant. I'm going to use a capital K for an equilibrium constant and a subscript EQ when I'm talking about equilibrium constants. And so let's say we have a reactant where we have reactant A combining with reactant B to form product C and D. Now the lowercase a, b, c's, and d's as coefficients are showing what you'd have in the balanced equation. When I write an equilibrium constant expression, that equilibrium K value is going to be equal to the concentration of products over the concentration of reactants. Remember, it's always products over reactants when I write an equilibrium value. Now, I do take the coefficient in the balanced equation, and that becomes an exponent in my equilibrium equation. So I would have product C times its or to the exponent of its coefficient times the concentration of product D to its exponent of its coefficient over reactant A's concentration to its exponent A times concentration of B to its coefficient as an exponent B here. Now, the square brackets represent usually when we're dealing with equilibrium processes in a solution. We will use square brackets as a shorthand notation to represent molarity values. Now, if you recall what molarity was for concentration, molarity was your moles of your solute, which in this case is either A, B, C, or D, so the moles of that solute per liter of the solution mixture. So if I put in molarities, that will work very effectively. In some cases, you might see an equilibrium constant shown related to partial pressures of a chemical reaction, but right now I'm going to focus on molarities. Now let's look at a specific equilibrium reaction and the values before and after equilibrium has been established for the concentration of reactants to products. Okay, so if I have nitrogen gas combining with hydrogen gas to form ammonia gas, and if I have a balanced equation that has a 1 to 3 to 2 for the coefficients, let's write an equilibrium constant expression for that. Now remember, when I write an equilibrium constant expression, the KEQ value is equal to the concentration of my products over my reactants, but I must take each of those concentrations to the exponent of the coefficient that's shown here, to a 1, to a 3, or to a 2. So if I write this equilibrium expression, in fact, this would be a good time to maybe pause the video and try to write the equilibrium expression. And once you have finished pausing the video, start it again, and I'm going to show you the answer to this. When we write the equilibrium expression, I'm going to have my concentration of my products, the ammonia, and the coefficient was a 2, so I'm going to square that concentration. That's over the concentration of my nitrogen gas. Since I have a coefficient of 1, my exponent's just a 1 there, which we normally will not show. And the concentration of my hydrogen gas in molarity is going to be to the coefficient as an exponent of 3. Now, if I look at all of these concentrations, what I might have are some initial concentrations as I begin with just reactants, and I haven't formed any products yet. I don't want to use those initial concentrations to find an equilibrium value. What I actually want to have happen is I want to allow the reaction to reach equilibrium, and at that point I don't see a net change anymore in the concentrations of reactants or products. We're at dynamic equilibrium at that point, and even though I have the forward reaction occurring and the reverse reaction occurring, there is no net change because the rate of the forward and reverse process have matched one another at equilibrium. So if I wait until I no longer see a change in those concentrations and they've leveled off with respect to concentration changes as well as changes in rate, we would measure in this case that we had a concentration at equilibrium, and notice the subscript EQ here for each of our concentrations at equilibrium. The nitrogen gas is 0.0600 molarity, the hydrogen gas is 0.180 molarity, and the ammonia gas is 0.280 molarity at equilibrium. Now if I use the equilibrium values, I can calculate what my equilibrium constant would be, and I would end up putting in the ammonia as 0.280, but I'm squaring that value because of the coefficient of a 2. That's divided by the 0.06 molarity of the nitrogen gas and the 0.180 molarity of the hydrogen gas. Since the hydrogen gas has a coefficient of 3, I take that to the third exponent there. When I calculate this equilibrium constant value, I get a value of 224. Now when I see a value for the equilibrium constant which is greater than 1, such as we see in this case being 224, that shows us that at equilibrium we're favoring the product. So we end up having more product present than we have reactants at equilibrium, and that's exactly what we're observing in this case. So if I asked you if we were favoring reactants or products, we can see at equilibrium we have more product that has formed than the reactants that are still present, so that would tell me to expect an equilibrium value greater than 1. We can tell that it's not a really huge number. It's not to a very large exponent for the equilibrium value, because if that were the case, I'd see hardly any reactants present. In this case I do see a little bit, so we expect to have a value that you might have seen, like in this case, in the hundreds for the equilibrium constant. So there's some general rules we can take away from this. When I look at an equilibrium constant, the magnitude of its value tells me some very useful information. So this would be something important to write in your notes. An equilibrium constant value that is much greater than 1 tells you that you're favoring the reaction going to the right. That means forming the products as you're going from left to right with the reaction as written. So products are favored with large equilibrium constant values. Now if your equilibrium constant is quite a bit smaller than 1, so if you have a very, very small equilibrium constant, sometimes that might be with scientific notation to a negative exponent. In that case, your reaction would lie to the left at equilibrium, meaning that you would still have a large quantity of reactants present and would have formed very little product once your reaction rates have matched one another. In that case, we would say the reactants would be favored. Those are the compounds listed to the left-hand side of your reaction arrow. If our equilibrium constant is very close to a 1, that tells you have a significant amount of reactants and products present all simultaneously. So our equilibrium, we could say, lies in the middle of this chemical process, so we should have similar amounts of reactants and products all present at the same time. So let's look at this visually. Let's look at some diagrams that would indicate small samples that have reached equilibrium. So here we have an equilibrium process where we're going from blue atoms or molecules to red atoms or molecules. In this case, we have at equilibrium very little of the product. So if we say that the blue spheres are reactant A and the red spheres are product B, in this case if we have products B over reactants A, in that case we would see that we had a ratio. If the exponents were just a 1-to-1, if the coefficients were just 1s here, we would have just one product molecule or atom, the red sphere, over 49 of the reactant atoms or molecules. So that would be 1 over 49 for the equilibrium constant. So we get a value of 0.020. So that's indicating when I get that small equilibrium constant that we're favoring keeping most of our reactants present at equilibrium and having very little product forming. Okay. Now let's consider the other scenario. Let's say that we have this orange sphere as a reactant and the products are these light green spheres. In that case, we have the opposite scenario where the product's still over the reactants, but I have 49 of my product molecules or atoms over just one of the reactant molecules or atoms at the equilibrium. And so that would in this case be favoring products quite a bit. So the equilibrium constant being listed as products over reactants in this case, if the coefficients are just 1-to-1, gives us an equilibrium constant of 49. So the larger the equilibrium constant becomes, we can see that the less and less of the reactant species is present at equilibrium. Okay, so we're favoring forming product in this case as that equilibrium constant becomes larger. Now, if we were to end up with a third scenario, so if we have these navy blue molecules or atoms going to these green molecules or atoms, and if we have a similar amount of each, so let's say we actually have at equilibrium equal amounts of both of them. If we were to look at the equilibrium process, and if we're still looking at coefficients of just 1-to-1, well, then we'd have 25 product molecules or atoms over 25 reactant molecules or atoms. We'd have a case in in this situation where we have an equilibrium constant that is perfectly 1. We won't necessarily always have a value that's perfectly 1, but if the equilibrium constant is near to 1, that may indicate that we have significant quantities of both reactants and products present at equilibrium. Okay, so these are some important things to realize. So just to review, if you have a small equilibrium constant, let's say we had an equilibrium constant that was 1 times 10 to the negative 30th. In this case, that's such a small equilibrium constant that we expect that we have formed very, very little products. So if you end up with an extremely small equilibrium constant, such as this one to the negative 30, for the exponent, then we expect that it yields very, very little product, and if it's small enough, such as it is, if it's to the negative 30th, we can expect that there's so little product formed, you could argue there's no significant reaction. So you might say there's no reaction at all that's occurring. Now, if we end up with a very large equilibrium constant, say my equilibrium constant is 2.2 times 10 to the 22nd, so if it's a really huge equilibrium constant, so if your K value is much, 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 much greater than 1, this would indicate that the reaction yields at equilibrium mostly product and hardly any other reactants left over. In that case, I might argue that this reaction goes pretty much to completion. It forms all product and has very little leftover unused reactant. Okay. Now, if my equilibrium constant is quite close to 1, though, then that's where we say both products and reactants are present in significant quantities at equilibrium. Okay, so those are some things to think about when you're looking at equilibrium processes. Now let's look back at our equilibrium process between nitrogen dioxide and dinitrogen tetroxide. So if I write this reaction going the other direction, so let's say we started with nitrogen dioxide forming dinitrogen tetroxide, and if I wanted to write an equilibrium expression for this reverse process of what we had looked at before, so I'm going from nitrogen dioxide to the dinitrogen tetroxide, well, when I write it this way, the equilibrium constant for this reversible reaction will still show products over reactants. So I'm going to show the dinitrogen tetroxide on the top of the expression in the numerator, and in the denominator, the bottom of my ratio, I'm going to see the nitrogen dioxide. So when I write the equilibrium constant, I have N2O4 over nitrogen dioxide. Since I have a coefficient of a 2 for the nitrogen dioxide, I have an exponent of a 2 for the nitrogen dioxide. Now, if I want to calculate an equilibrium constant for this reaction, well, I have to wait until the reaction reaches equilibrium. Now remember, how do we tell if a reaction's at equilibrium? What things do I look for? Okay, let's ask yourselves that. So the local instructor should see if you have a good answer for that. Now, what you should realize is at equilibrium, we no longer see a net change in the concentration of reactants or products. There's also another way to tell we're at equilibrium. It's where the rate of the forward reaction now matches the rate of the reverse reaction. That's why you no longer see a net change in the quantity of reactants or products at equilibrium, even though it's still in a dynamic equilibrium with the forward and reverse process happening. It's happening at an identical rate. So I have no net change. So if I wait until the concentration of the dinitrogen tetroxide is maintained at 1.25 molarity, I can say that's at equilibrium if I'm not seeing a net change anymore. And if the nitrogen dioxide is maintained at a concentration of 0.0750 molarity at equilibrium with no net change, well, in that situation, I can plug those molarities into my equilibrium constant expression equation and calculate an equilibrium constant. So if I go ahead and do that, I plug in the molarity of my products over the molarity of my reactants. Remember, since the coefficient is a 2 for the reactant here, I need to square that molarity. But I calculate the equilibrium constant is a value of 222 at this temperature and this set of conditions. Now, since that value is greater than 1, that tells us we're favoring forming the products. We're favoring going to the right-hand side for this chemical reaction to form dinitrogen tetroxide. So we have more products on the right at equilibrium than we would have reactants. Okay, that's actually what I observed, right? At equilibrium, I had 1.25 molarity of the dinitrogen tetroxide, and the nitrogen dioxide was only 0.0750 molarity. So I was definitely at equilibrium in this case. Okay, so if I were to describe the position of equilibrium, I'd say I favor forming products as the reaction is written. Okay, because that equilibrium constant is larger than 1. So I favor the right-hand side of this equilibrium process. So equilibrium lies to the right. Okay, so let's consider let's consider a chemical reaction that has an equilibrium constant equal to 4. So here I have disulfur dichloride reacting with diatomic chlorine gas to form sulfur dichloride gas. Now, if we started with the following initial conditions of reactants and products, so initially, so this is not at equilibrium yet, we had 0.10 molarity of my first reactant, 0.10 molarity of my second reactant, and we had it in the mixture initially some product, sulfur dichloride, of 0.30 molarity. So if I have all of these initial concentrations, but I have not reached equilibrium yet, I can maybe start to make some initial predictions about what would happen to my concentrations. So let's say I want to decide what's going to happen to my concentration of my chlorine. Now this equilibrium constant's of 4. Now that's greater than 1. So you might argue that we're favoring products, but we're only favoring products very slightly here because that equilibrium constant isn't that large. We're still somewhat close to 1, so we should still have a reasonably large amount of both sets of equilibrium concentrations. Okay, so to decide if whether the system is already at equilibrium when we begin with, we can go ahead and predict the direction the reaction will proceed to reach equilibrium. Okay, what we can do is we can substitute the concentrations in the equilibrium constant expression for what we actually have initially. Okay, and compare that to my equilibrium constant. Okay, so my equilibrium constant was defined as 4. So if I write the equilibrium constant expression, I have products over reactants. Since my coefficient was a 2 for the products, I'm squaring that term. Right? The coefficient for the reactants were 1s, so I just have a 1 for each of those terms. Now, if I plug in my initial concentration, so be careful, even though I'm still using the equilibrium expression that we had, this will not be an equilibrium constant because I'm going to put in the initial concentrations before we've reached equilibrium. So if I put in the 0.3 molarity of the product squared over the 0.1 molarity of each of the reactants that I'm multiplying in the denominator, I get a value of 9. Okay, now sometimes this is called a reaction quotient expression. The reaction quotient expression is calculated almost like an equilibrium constant, but it's for non-equilibrium values. Now, if you were to find those initial concentrations gave you a value of 4, we could say we were already at equilibrium. In this case, the value is not 4. It's greater than 4. So that tells us I actually have more product than reactants than I would have at equilibrium because the value is too large at the initial concentrations. So if I see this reaction quotient value, if the 9 here is greater than the equilibrium constant value, that tells us we're going to have to decrease the amount of the products and increase the amount of the reactants before I reach equilibrium. That tells us that the reverse reaction will have a faster rate initially than the forward reaction. So I'm actually going to form more of my reactant species and consume a little bit of the product species before I reach dynamic equilibrium again. Okay, so I'm going to have my value, since it's not equilibrium, have to shift back towards the left to form more of my reactants until this ratio is equal to the equilibrium value that we were told was 4. Okay, so there's too much product and not enough reactant to be at equilibrium under this situation. So the reaction will proceed in the reverse direction until we do reach equilibrium. Okay. So in this case, since the reaction proceeds in the reverse direction, we're going to end up seeing the concentration of the chlorine gas increasing while the concentration of the sulfur dichloride will decrease until that ratio is no longer 9, but the molarity ratios reach a 4 for the equilibrium constant expression. Okay. So that's what needs to occur in order for this number to drop. I must decrease my value for my concentration of my products and increase my value for the concentration of the reactants in order for my reaction quotient value at those concentrations to match the equilibrium value of a 4. Okay. So let's practice writing some equilibrium constant expressions. So what I'd like you to do is look at the following reaction and try writing an equilibrium constant expression for it. Now, before we get started, I need to give you a warning. When I look at pure liquids or solids in an equilibrium constant expression, we consider that the molarity of their concentration in the solution isn't significantly changing for solids or pure liquids. Okay, so in this case, I will exclude the solids. So go ahead and write the equilibrium constant expression with the solids excluded for magnesium and magnesium oxide. Okay, so if you've paused the video and then you've started it again now, I'm going to give you the answer to this equilibrium expression. So since the solids are not included in the equilibrium expression, we end up with the products of carbon monoxide over the reactants of the carbon dioxide, and that equilibrium expression will be related to those two molarities. Again, I exclude solids or pure liquids from an equilibrium expression, so that's something new that we're seeing now. So let's try this one more time. Let's say we're looking at lead 2 chloride dissolving to form in water lead 2 cations and chloride ions. Now normally you've learned with your solubility rules that lead 2 chloride is insoluble, but to be honest, even your insoluble compounds will dissolve to a very small extent in water-based solutions. So in that situation, we're going to have just a little bit of my lead 2 cations and my chloride ions that has dissolved in water. In fact, this tends to become more soluble, the lead 2 chloride becomes more soluble as your temperature of your solution increases. Now, when I write an equilibrium constant expression for this situation, remember I'm still going to leave the solid out of the equilibrium expression. So solids and pure liquids are left out, and then the species in solution are going to be shown. Now, when I have a insoluble compound, and I'm looking at how much will dissolve into solution, sometimes we'll call this a KSP value, a solubility product calculation. But the solubility product is basically just an equilibrium constant as well. So if you see a subscript SP, it's still an equilibrium expression. And if you've written the correct equilibrium expression for this, we're going to see the concentration of the lead cations times the concentration of the chloride ions squared. Okay, so what I would like you to do if you have any additional time today in your class is go ahead on Connect, and I'd like you to practice the homework questions related to writing correct equilibrium constant expressions. Okay, and then predicting what equilibrium constant expressions are telling you with respect to favoring products or reactants. Okay, have a great day, everybody.